Because I have an ambitious plan of doing all the solutions so that they're all in the recording. I said I was going to take requests because I said, oh, there's no way I could possibly do all of those. But we're going to do it. Did you get my message yesterday? Wasn't really last night, yesterday afternoon. So I posted a comprehensive, I want to highlight that this is practice 4 test 2. Let you see lots of different options. The actual test is going to be shorter, of course, but if you can work through all of these, then you're set.
Will there be like a solution posted for this? Or?
We're going to do them now together. All right. So just to look at me listing all the core concepts. These are things, so just like a little checklist of things that you should know. We're not going to read through them because we're going to actually work through the problems. There are a couple of things that I decided not to test on, like the binary search algorithm, for example. It is something we talked about, but I'll leave it for someone else to test, for example. But the other ones, I think that's the only thing. We'll see if anything comes up. But oh yeah, we talked about multiplying matrices, but I'm not going to make you do it. So it still made the list, but you don't have to do it. But we did talk about it. Okay. So I started earlier today. I thought, oh, I'll start making the solutions. Look at me go. But that's when I decided, you know what? I think we can do it just working together. So practice problems. First one is from chapter 6. So I give you a directed graph of some relation. And first I ask you to write the adjacency matrix for this relation. Okay. And so what I'm going to do is I'm just going to snag all the pieces and put them together down below. And so, like I said, I did start, and then I thought, nah, we can do it. So for me, I think it's helpful when I rewrite the directed graph as a list of ordered pairs, because for me, that's just easier to look at, right, than this directed graph. You don't need to do this. In fact, maybe I'll write that this is, of course, optional. Wait, maybe not. All right, so here, this is optional, but we have a relation from 1 to 2, 1 to 3, 3 to 2, 3 to 4, and 4 to 3. And so I just list those ordered pairs. What's another way that you could have been given this information? As a list of ordered pairs, right? And then I ask you to draw the directed graph or the digraph. Could go the other way, right? And so just be prepared for that, I guess. Write the adjacency matrix for this relation. And so I read it as from the rows. So from these to these. Okay. So from 1 to 2. From 1 to 3. Why does it matter which one's which? Well, because there is no relation from 3 to 1, right? So it's important that you have an order that you're doing it. You could have switched these up as long as you're consistent, right? Because then you can flip your matrix and it would be the same. So, but I'm going to say from here to here. And that's the typical setup. From 2, but 2 doesn't have any arrows going out. And so it's just a row of zeros. From 3 goes to 2 and from 3 to 4. All right. 4 just goes to 3. Is the relation R symmetric, anti-symmetric, or neither? Right. So, and then of course you have to explain. It's not symmetric because if it was symmetric, we would have these little loops everywhere that there's a one-way street, there would be a street going back, right? Then it would be symmetric. Okay. So my argument there is R is not symmetric since not all relationships have a two-way relationship. For example, and then it's always nice to back it up with an example. For example, 1, 2 is missing 2, 1. So 1, 2 exists, right? The map from 1 to 2, but I guess how I wrote it is kind of weird. 1, 2 is missing, maybe I'll say the relation 1, 2 is missing the road back to 1, just to clarify. All of a sudden I'm talking about roads, I guess. I'll call it a relation. Yeah. What does it mean to be anti-symmetric? Anti-symmetric is when there are no loops like this, right? So there are only one-way streets, but it's not anti-symmetric because we have this little symmetric situation between 3 and 4, right? And so what I wrote was R is not anti-symmetric since 3, 4 and 4, 3 exists, right? There's that map between 3 and 4. Is the relation R reflexive or not? What does it mean to be reflexive? It means that we have a map, a self-loop on every vertex. We don't have any self-loops, and so it can't be reflexive. No. Since there are no self-loops,
Just one self-loop? Or
they all have to have self-loops. It can't be reflexive. And I am gonna write that. All vertices must have self-loops, just to clarify what the condition was. Okay, let me grab D. Transitivity is tricky. Remember what transitivity is? So we want to know if it's transitive or not. It means that I could figure out a one-way flight that would replace a multiple-way flight, right? A problem is I could get from 1 to 3 to 4, but I don't see a direct flight from 1 to 4. So it's not transitive, right? So a lot of these cases, you just have to find one kind of opposing example, and then that's good enough.
wait,
Okay.
transitive also just for something to be transitive, does every node have to, you're not notified, does every verse have to connect to itself or to every other verse?
Basically both. Usually what ends up happening is to be transitive, you end up usually connecting each of the vertices and the self loops. Because I could go from 1 to, I guess in this case, I couldn't get to, that was a bad example. So I can't get back. So I wouldn't need a self loop on 1 because I can't get back there with any flights. I would need a self loop on 3 because I could start at 3, go to 4, and then go back to 3. So then I would need a self loop here, for example. Same on 4. Yeah. Because I can start at 4, go to 3, go back to 4. Oh. Don't worry, we're gonna answer that. But we'll start with, is it transitive or not? No, it is not transitive. Since there is no 1 to 4, or maybe I'll use the ordered pairs. There's no 1, 4, but I could go 1, 3, 3, 4. All right, so I could go from 1 to 4 that way, but there's no 1 to 4. Okay. Let me add a page here. Is R a partial ordering, an equivalence relation, or neither? Explain your answer. All of these are just taking definitions and applying them to this example, right? What does it mean for it to have a partial ordering? It means that it has to be, and I always mix these up, antisymmetric, reflexive, and transitive, right? I think. Should have confirmed. Partial ordering. Can someone confirm that that's it? I'll find it. I don't want to write it in. Did I write it in here? Maybe. Too wordy. Let's see here. Where is it? Okay. It is antisymmetric. I guess I shouldn't doubt myself, but it's healthy. So partial ordering is reflexive. So already we know it's not a partial ordering, right? But you do have to explain your answer. So you have to explain why it's not a partial ordering, right? And so it's reflexive, antisymmetric, and transitive. We just established that it's none of those things, right? And so R is none of these, therefore not a partial ordering. How about an equivalence relation? That's the same, except the only difference is it's reflexive, symmetric, and transitive. And so if it's reflexive, symmetric, and transitive, well, we also said that R is none of these, right? We decided it's not antisymmetric, it's not symmetric, it's not reflexive, it's not transitive. And so R is none of these, therefore not an equivalence relation. Therefore, it is neither. Right. And justifying the other two, why those don't apply, obviously, is enough for saying that it's neither. Okay. Good. Don't need to underline that. Okay. Closures. Uh-oh. It's fine until we get to the closure with respect to transitivity. That's where I always bung it up. But if we want to find the closure with respect to reflexivity, that's where we figure out what points are missing or what relations are missing. And I'm going to bring this in here to make it reflexive. To make it reflexive, right? If we can get from a starting point back to the starting point, then we need to have a self loop, right? And so, or no, they all have to have self loops, all of them. I was talking about transitivity. They all have to have self loops. Mix up my direction of my self loop. Counterclockwise. I'll get really wild.
Like every relation for it to be reflexive, all vertices have to have self loops.
Yes. And so we would need to add 1, 1, 2, 2, 3, 3, and 4, 4 is the closure with respect to reflexivity. So this here is the answer, right? That's the closure. And we use R plus for the transitivity, but I don't know if there's established notation for closure with respect to reflexivity, but closure with respect to reflexivity. Squeezed it in there. Okay. How about the closure? What's the next closure I wanted? Symmetry. That one's fun. Says I. I think it's the easiest one. I'm gonna copy this here. On the test, when I make you do these closures, do you want the digraph again so that you can draw on it? Or, well, I guess I'm taking requests. Or do you prefer that I give you the ordered pairs and then you have to draw the digraph? Ooh.
Diagrams better. Yeah, diagrams.
Start here.
It also causes a lot less confusion because people are gonna draw like its relations different.
I know. I guess even if I made you draw it, I could put the vertices where they're supposed to go and then you draw the connections or something. I'll see if, yeah. Okay, symmetry. Symmetry says if there's a one-way street, I need to have another opposite way street. That didn't make sense. This one's all good, right? But from 3 to 1 is missing, from 2 to 1 is missing, and from 2 to 3 is missing. I think that's it. So the closure with respect to symmetry would be, and now I'm going to list all these. 2, 1, 2, 3, and 3, 1. Okay. Last one. Well, of this part or this question copy, transitivity. Uh-oh. So this is where it would have paid off, sort of, to use matrix multiplication. And if you want to learn the matrix multiplication way, then go for it. It's in the textbook, and you can do it. But to me, I don't know. It's not worth the trouble of learning matrix multiplication and learning to find the closure with respect to transitivity, which involves, I think, 4 multiplications in this case, which is terrible because you'd have to find r to the power of 4. I know. That's so Paul. He loves that stuff. Yeah. I told him that I skipped matrix multiplication. He's like, yeah, maybe that's what I'll do too. He's like, I usually do it. Yeah, I know he usually does it, but he's a funny guy. Yeah, I told him where we were at in the course, and he's like, what? No, I'm way behind, which felt pretty good. Yeah, I'm like, you gotta cut all that fluff you don't need. Transitivity. Okay, here we go. So let's get those self loops out of the way because they trip me up. So I need to do those right away. So if I can get from 3 to 4 back to 3, then I need a self loop because I need a direct flight from 3 to 3. Now, I don't see a way to get out of 2, which means I can't get, there's no, ooh, well, there's no self loop because I can't get out of 2. No self loop because I can't get out of, or I can't get into is what I meant. Ugh, words. Can't get into 2, I can't get into 1. So that's fine. So I just need a self loop on 4. Okay. Now this is that tricky part where we add all the links that are missing. And between you, me, and this Zoom recording going on YouTube, I'm going to be pretty lenient on this stuff when I'm marking. So just try to find all of them. But it's really hard without the matrix multiplication. So that's, yeah, I'm okay with that. But just try to find as many missing links as you can. Okay, so we already found earlier, we found I can go from 1 to 3 to 4, which means that I need to have a direct flight to 4. I can go from 1 to, I'm done with 1. Why? Because I have a link to all 3 other vertices. So then I'm going to back off of 1 for a little bit. How about 2? I can go from, nope. Can't leave 2, so that's okay. How about 3? 3 is going to make a mess. I can just tell. There's so many roads in and out. Yikes. Okay, I can go from 3 to 2, but I can't get out, so that's okay. I can go from 3 to 4, and then 4 to 3, and then to 2, but I already have a 3 to 2. Okay, so that's fine. maybe it's not so bad. And that's what I say. Is that all of them? Do you see any more?
I was thinking is 3 to 1 not transit?
What, so from here, I can go to 2, but I can't get to 1. So I can go from 1 to 3. Maybe there is just the 3.
What's a good quick definition?
The loose definition is if there's a multi-way flight that you could take, you also have to add a one-way, a direct flight. If you think about flights, which makes sense, at least to me, for how I think about it. Do you see any more? I guess I should check Zoom. Maybe they're seeing something. Uh-oh. Everyone got nervous. Oh. 4, 3, 2. Okay, nice. Let's see here. 4, 3, 2. Hey. Thank you very much. Yeah, sold. They're out there. I'm not good at finding them. I'll check the chat again to see if you have any more nuggets for me. No. Well, maybe you do, but I can't see it now. It's game over. Closure with respect to transitivity. Is, let's do these. Let's do 3, 3, 4, 4, 1, 4, and 4, 2. I want to do red. I'll just say any missing. Mostly for me, I might forget to go back to it. But there are online calculators that'll just tell you what it is. So you can always check it, but not on a test, obviously. So that makes it hard. Okay. Nice. Question. Whoa, weird. Question 2, 3. Why did it print like that? Oh, I know why. I did something weird. That's question 2 there. They might, all the numberings might be off. I'll do 2/3 because then it picks up at 4. I have an empty question sitting here and it doesn't know what to do. That's okay. Okay. The matrix representing a relation on the set A, B, C, D is given as this adjacency matrix. So now we have to draw the diagraph for this relation. Uh-oh. Now, the rest of these are the exact same parts, which should be some sort of clue as to what you can expect on the test, right? Just be able to do all these given some relationship or some relation. Okay, so what I want to do to make sure that we get through all the solutions, we're going to draw the diagraph. I don't know why I said it like that. And then I'll add the solutions to the rest of the parts after class, or we'll go back to it if we have more time. But Just want to make sure that we cover all our bases, right? Because this is just more of the same, more practice. So the matrix representing this relation is here. Now we want to draw whoa, why do I keep saying that? Digraph. So first thing I'm going to do is just jot down, right? A, B, C, D, A, B, C, D. And just remember that we're going from here to here. Okay. That's going to be important in our ordered pairs, which for me, again, I'm just going to write out the ordered pairs, right? And then that's going to be my kind of gateway here. So I have no point at AA, so no self loop at A. I do have an edge going from A to B. That's the first one. I see no other things at A, so then at B, I have an edge from B to D. And sometimes I'll cross these out as I've done them just to kind of remind myself where I'm at. I have nothing from C, which means C is going to be a little lonely, but that's okay. I have D to A and D to C. Finally, something with C. D to A and D to C. All right. Again, this part is optional, but I do find that it's quite helpful. Because reading that is hard. Okay. So, digraph. First thing I'm going to do is plop down A, B, C, D. Now you're allowed to make changes as you go, but we can kind of get an idea of what it's going to look like by thinking about A to B, and then B goes to D, and then D goes to A, and then D goes to C. So I might do something like A, B, let's see. Sure, C, D, something like that. And my points or my vertices later, fill them in. Okay. And we might have to change it later, but that's okay. So I need a line from A to B. So from A to B, that one's done. From B to D, which means it's going to go like this. From D to A, and from D to C. And that's it. Right. And now you're back to where we started in the previous question, right? And what's the only thing that's popping out at me? Well, it's not reflexive because there are no self loops. It's not symmetric because there are no back and forth, which means what? It means it's anti-symmetric. Nice. But I'll leave those. So I'll leave this page blank and fill those in later, or if we have time at the end of the class. Because we've got functions to deal with. Oh, and I need another page. Consider the two functions defined on the set A, B, C, D given by F, which has a relation from A, B, B, D, C, A, D, C, and G, A, C, B, B, C, A, D, D. Find the following. F composed with G at A. Okay? And these compositions, you just want to be really careful, right, when you're working back and forth. And you always want to start in the middle here, right? And so you want to find G of A first. Now, G of A is from the function G, you give an input A, and G of A is the output, which is C. So this is going to be F of C. F is the function, which points me in this direction here. Now, if C is the input, A is the output. So F of C is equal to A. So F composed with G of A is equal to A. I guess we should have made sure that these were functions, but we're told that they're functions. But just for practice, let's think about, are these functions, right? We have to have an output for each possible input for each of them. A, B, C, D, that's good. A, B, C, D, right? And so that's good. And because there's only one input output combination for each value on the set, then I know it can't be a non-function, because to be a non-function, that didn't come out right. I would have to have two values where A goes to B and A goes to C, for example, then it's not a function, right? It has to map to a unique value of in the output. They're allowed to map to the same output, but in this case, none of them do. And that's okay. Same thing, G of F of C, right? So how you read these compositions, I think the easiest way to read them is G of F of C, making sure you start in the middle or in the very center. Then you want to find G of, but F of C, F is the function, C is the input, A is the output. So you're trying to find G of A. So now G is the function, A is the input, C is the output. We can do function composition with the function itself, right? F of B. So now I want to find F of, but F of B, so B is the input, has an output of D. So it becomes this kind of doo-doo. F of D, so now D is the input in F, which has an output of C. The inverse, G inverse of A. You could rewrite all of these, right? You could, if you wanted to, figure out what F inverse looks like. But what are you doing? You're just going to reverse. The output is now the input and the input is now the output, right? And so you could rewrite this as BA, DB, AC, and CD. And you could do the same thing for G. You don't have to do that, but if you find it's helpful, right, when you need to work with the inverse of the function, then maybe it's nice to have it just have all four of them listed. Yeah. What I'm going to do is G inverse of A, the inverse works from the output and produces the input. So now in G, I need to find the output where the output is A, and then the result is the input, which is C. It's always C, I guess. Okay. G inverse of F of B. So starting in the center, we want G inverse of F of B. So F of B is D. G inverse of D. So now I'm looking at G where the output is D. Now D is from an input of D, so confusingly, it's a D. F inverse of G inverse of C, we're going to start with the G inverse of C. So I have an output of C, then G inverse of C is A. So F inverse of A, the output is A when the input is C. Can you believe it? C. Okay. So as long as you have those ordered pairs, which I will give you, then it's not so bad, those function compositions. Easy for me to say, I guess, but. Consider the relation on the set 1, 2, 3, 4, 5. So those are all my possible inputs in my domain, defined by this F from 1 to 2, 2 to 3, 3 to 5, 4 to 5, and 5 to 1. We want to explain why F is a function from A to A. One of the things that you could do if you find it helpful, again, this part is optional, but what you could do is you could say, okay, if I have something from A onto A, I shouldn't say onto because it's special, but then I have to have from 1, 2, 3, 4, 5. And then the possible things that I could map to are 1, 2, 3, 4, 5. What we're looking for is to be a function, each of these values have to have some activity, but only once. Right? So here, and just for some, this is the domain, and this is the codomain. Each value in the domain must be mapped from exactly once. That's what we're looking for. So then F is going from A to A. So we can draw these. I'll use a different color. 1 goes to 2, 2 goes to 3, 3 goes to 5, 4 goes to 5, and 5 goes to 1. Of course it does, to chop all these up. Make it extra confusing looking. I have an idea to make it not look so ugly. I'll just put 5 up top. Now that I've seen it, I can do that and know that it's a little bit cleaner. That was weird of me, but I just can't stand that line going through, right? And it's just to help us visualize. Okay, so each point has an arrow leaving it, so that's a good start. Another thing that we're looking for is that we don't have something more than one arrow from each point, right? So exactly once. And so that's why it's a function. F is a function since each value in the domain is mapped from exactly once. Now this part is optional, just like I said. You could look at this and just make sure that each value in A has an output and only appears once. You can do that, right? So you don't need to show it like this, but I find it's helpful. Let's make a side note because I think I forgot to add it as a part. So let's add it. What could I possibly be adding, you ask? So if this is the domain and this is the codomain, then the range is the list of the values that are actually mapped to. And so that's the difference between the codomain and the range, is that, so then the range, so versus the range, which is in this case 1, 2, 3, 5. Since 4 is not mapped to. And 4 is in the codomain, but it's not in the range. Right, so that's just the slight difference between the two. Usually we don't talk about the codomain, we only talk about the domain and range. And that's probably why. Okay. Good. F is a function. That's great. Is F onto? Explain. Well, then you better know what it means to be onto. What's it mean to be onto? It means that every value in the codomain has to be mapped to, but that's not true. And so that's where I find it's easier to visualize it. But again, you could have just gone from here and said, okay, I have an output of 1, 2, 3, 5, 5, 4 is missing, right? You don't need to see it like this, but I find that it's helpful. So no, F is not onto, which is also called injective. Do you prefer injective, surjective, or onto, one-to-one? I like onto and one-to-one because it kind of guides me to what I'm looking for. Is everything mapped onto? Fine, I'll stick with my onto, one-to-one. No, F is not onto, since 4 is not in the range. Incorporating our fancy terminology. It's in the codomain, but not in the range. Sure, we'll show off even more. Is in the codomain, but not in the range. Now we're cooking with gas, huh? Okay. Is F one-to-one? Well, that means we have to know what it means to be one-to-one, of course. It's like an entire test of definitions, but also being able to apply them. Yikes. So many. 1-to-1. Well, visually, what does it look like? It means that each input maps to a unique output, right? And that unique output maps back to only one input. But the problem here is 3 goes to 5 and 4 goes to 5. So it's not 1-to-1. No, F is not 1-to-1. Since 4 goes to 5 and, oh, I lost it. No, sorry, 3 goes to 5. Not that it matters, but since 3 goes to 5 and 4 goes to 5, 5 is mapped to twice and can't be mapped back to, and can't be mapped back to, and I just need a little bit more room, to a unique input. Right, if I'm going back from 5, there's no way of knowing if I have to go to 3 or if I have to go to 4, right? And so it's not 1-to-1. Okay. What's the inverse of F? We already saw how to do that, but let's do it again. I'm also going to grab F here so that we have it. F inverse. We take each of these and we just switch the input and the output to 1, 3, 2, 3, 5. Oops, I almost didn't switch them, or I didn't switch them. 5, 4. Oh. Oh. 5, 3. Okay, nice and slow, Emily. 5, 4, 1, 5. Man, that's hard for some reason. Just making sure. I think I did it. I'm making you find the inverse, but actually isn't going to have an inverse because it's not 1-to-1, but you did what you were asked, and that's fine.
Wait, would the inverse not be a function since 5 is going to do different things?
Exactly. So here, just as a side note, I'll write it in red because probably an oversight on my part. Or I was just going crazy with adding the parts. F inverse doesn't actually exist. Since F is not 1-to-1. The function has to be 1-to-1. Back to that problem of it. If I'm sitting here at 5, right? Sitting here at 5, do I go to 3 or do I go to 4? Right? And so here, this is not a function like you just said, right? And so here, not a function. That's not something that I need you to be aware of, right? All I asked you to do was find this blue part, and that's all I'm expecting you to do, right? But it's nice to see it for some more practice. Okay. And like I said, probably an oversight on my part. Oopsies. Or maybe it was intentional. A teachable moment. Uh-oh. Nope, it was definitely an oversight. we can't because it's not, oh, combining my words, because F is not 1-to-1. How about no, I can't cut it. I could map it to something else, I guess. What would you have to do? Sorry. I know where it came from. Came from the final exam where it is 1-to-1 and you can show that it's actually the inverse, but then I changed the function. I didn't check it. So here we would show that f of f inverse of some x, so any input, is equal to x, and f inverse of f of x is also equal to x, right? Applying that same practice that we were doing earlier, right? You can go through each value, so each input, 1, 2, 3, 4, 5, and I would only use one, right? Say there, that shows it. So for example, 5's the troublemaker, but if I do f of f inverse of 1, then I get f of the inverse 1 is 5, looking at the inverse function, right? Or you can go straight from here and say, oh, the output is 1, then I get a 5. But then I get f of 5. F of 5 is 1. Right? The other way, f inverse of f of 1, right? It has to be, so the input has to be the result. If we've taken a function and then done the inverse, which is basically it's reversing it, then it has to be just the input. F of 1 is 5. Five's the troublemaker. F inverse of 5, I can't do it. Right? I'm sad because is it equal to 3 or is it equal to 4? I'll be more careful. Maybe I'll alter your, what would I need to do? I could map 3 to 4. All of a sudden it's 1-to-1 and onto. That's kind of boring. But, right, the only change I would need to make here is instead of 3 going to 5, I could go 3 to 4, and then it would change the inverse just slightly, right? Now you'd have 4, 3, and then you can go through and you can check them all. But good thing we did all the other compositions, and then you know what to do. It's not very reassuring, is it? Put a little red X. I'll fix that. Okay. Which of the following relations on 1, 2, 3, 4 are functions? Explain why it is or is not a function. 2 checklists, right? each of 1, 2, 3, 4 have to be listed as inputs, right? 1, 2, 3, 4. So that part's good. So here, each of 1, 2, 3, 4 as input. Here, that first one, that's true. But I can only have exactly once. No. Because 1 is going to 1 and 1 is going to 2, so it's a relation, but it's not a function. Not a function. Try to squeeze them in. Okay, let's see here. Make some room. Uh-oh. Uh-oh. Function? No. One, 2, 3, 4. That's good. And exactly once. Ding, ding, ding. Looks good. All right. 1, 2, 4. So 3 is missing. Exactly once can't be true either. So no. 1, 2, 3, 4. Good. They're all listed. And exactly once. That's also true. So it is a function. Oops.
Wait, how is A not a function, but B is?
A isn't a function because I have 1 going to 1, but I also have 1 going to 2.
Oh.
And that's not allowed. Nice. This one sneaks under the radar. Find the inverse of this little function. F of x is 4x minus 3. To find the inverse, we need to find the function that undoes this thing. Okay. And so what I like to do is I replace f of x with y. And then I'm going to solve for x. The way I remember which one to solve for is I've already solved for y, so then I must be solving for the other one, right? I want to unravel this thing. Solving for x, I get y plus 3 is equal to 4x, which means that x is y plus 3 over 4. That's good. Now, here's where I do some kind of hand wavy stuff. And to write this as the inverse of f, so then this is going to be the inverse. And usually what we do, kind of confusing, is that we use x as the input for the inverse as well. If you wrote f inverse of y, that's totally fine because y is the variable here. But usually we do a little sneaky maneuver where we use the same input variable, which honestly is quite confusing. F inverse of x is x plus 3 over 4. right? Use x as the variable again. I guess another way you could do it is if you rewrote it as x equals 4y minus 3 and then solve for y. Either way, you're doing the same thing, so it doesn't. Prove the inverse you found actually is the inverse. We were just asked that and I'd set you up for failure because it wasn't 1-to-1, so there is no inverse. But in this case, it is 1-to-1 and there is an inverse and we found it. And to prove it, we have to use function composition. F of f inverse of x is equal to x. And so we have to show, and f inverse of f of x is also equal to x. So we need to show that f inverse of f of x is it equal to x. F inverse, and what I'm going to do is replace f of x with 4x minus 3, which is exactly what we were doing, but now it's a little function. F inverse of 4x minus 3. Which means that in this inverse function, right, instead of x, I'm going to replace it with 4x minus 3, treating that as one thing. So now you have 4x minus 3 plus 3 divided by 4. Looks promising, right? But we'll work through it. So I get 4x minus 3 plus 3 over 4, just rewriting it without the brackets. I use those brackets to show myself that 4x minus 3 is just one thing, but you don't actually need them. Then I can simplify in the numerator, -3 plus 3, that's going to go to 0. So now I'm left with 4x over 4. But of course, that's going to cancel. And I'm left with x. Whee! Which is what I wanted, right? It'll always dissolve to x, right? No matter how complicated. Don't worry, you'll notice it's the same format as that review sheet I posted when I was sick, right? You had to do one of these. It's the same format. It's going to be the same format on the test. It's going to be the same format on the final. So if you just do it like this, you're good. Oh, I did it in a different order. That's okay. So now we also want to show that f of f inverse of x is it equal to x. I'll do them side by side because otherwise it's just lines upon lines. So now I want to do f of f inverse is a little bit bigger, right? X plus 3 divided by 4. That's now my variable in f of x, which is 4x minus 3. So now I have this is equal to 4 times x plus 3 divided by 4 minus 3. Since I'm multiplying and dividing by 4, those are going to cancel. Oh, minus 3. It erased itself somehow. And all I'm left with is x plus 3 minus 3, which is x. Whee! Therefore, f inverse of x equal to x plus 3 over 4 is indeed the inverse of f of x is equal to 4x minus 3. Nice. Okay. Good. kind of fun once you kind of see what you have to do. Okay, I got it. And what I like especially about these is that you know it has to equal the input, right? You have to get there. So if you didn't, then you know that you probably did something wrong up here, and then you have to go back and fix it. Okay. That's the end of chapter 7. All right. On to chapter 8, which was recursion. And I am working through the chapters chronologically. And as much as I can, I'm going to try to do that on the test. It's just if space is weird, then sometimes I do a little switcheroo. But I try as much as possible to just work through how they appeared. Recall the recursive definition of the binomial coefficient. We have to assume that n is greater than or equal to 0 and k is somewhere between n and 0. And then we define n choose k by these base functions. N choose 0 is 1 and n choose n is 1. And the recursive definition of the choose function is n choose k. I can rewrite it as n minus 1 choose k plus n minus 1 choose k minus 1. And we're going to apply this to compute 5 choose 2. I think I got you to do 7 choose 2 or something crazy. I'm not going to go crazy. It's going to be, this is as big as it's going to get. So you could work through all of them if you wanted to prepare. There or more. So applying the recursive definition, n choose 1 is 4 and k is 2 plus n minus 1 is 4 still and k minus 1 is 1. Now I can apply that recursive definition to each of these, right? I wonder, I tend to go crazy with the brackets. 4 choose 2 becomes 3 choose 2 plus 3 choose 1 bracket. That's for this 4 choose 2. I still need to do 4 choose 1 plus, plus bracket. 4 minus 1 is 3 choose 1 plus 3 choose 0. Here's our first base case. N choose 0 is 1. So now we're going to be chipping away at these until they're all just a bunch of ones added together. And we're pretty close already. Focusing on the 3 choose 2, I get 2 choose 2, another base case, but in the other situation, right, n choose n, there's only one way to choose all of the things, and there's only one way to choose all or no things. So 2 choose 2 is equal to 1, so that's good. Plus 2 choose 1 plus, now I'm chipping away at the 3 choose 1. 3 choose 1 is 2 choose 1 plus 2 choose 0. Oops. 2 choose 0 is another base case. That's good. Now the textbook, if you follow the textbook, right, they condense this into 2 times 3 choose 1. So then you would just have a 2 out front here, and then you could expand it. I don't do that, and I'm not exactly sure why. I find it confusing, right? Then I have to stop and collect all the like choose functions, and I guess I'd just rather work through it. So then I have 3 choose 1, which turns into 2 choose 1 plus 2 choose 0, and then plus 1. This is also 1. But notice how now I have 3 times 2 choose 1. It's tempting. I'm not going to do it because I'm going to stick to my guns, but you're welcome to collect those if you want. So I get 1 plus 2 choose 1 becomes 1 choose 1 plus 1 choose 0. 2 base cases. Phew. Plus 1 choose 1 plus 1 choose 0 plus 1 plus 1 choose 1 over 1. 1 choose 1, 1 choose 0 plus 1 and bracket. But this is 1, this is 1, this is 1, this is 1, and this is 1, and this is 1. So I get 1 plus 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 1. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Really hoping when I check it with my calculator, which I definitely encourage you to do, 5 choose 2 is 10. Phew. You could check on your calculator. Or by the definition of the choose function, n choose k is n factorial over k factorial over n minus or times n minus k factorial, which means you have 5 factorial over 2 factorial times 3 factorial, but that's 5 times 4 times 3 factorial over 2 factorial, 3 factorial. That 3 factorial cancels. 2 factorial is just 2 times 1, so that's just 2. So now I have 20 divided by 2, which is also 10. Right? If for some reason you just hate your calculator, you don't need it. Right? Okay. My check on my calculator got longer than the actual calculation, I guess. It's faster, but looks the same. Okay, good. Recursion. Okay, I've got some polynomial. And start it on a fresh page here. We've got some polynomial x to the power of 6 minus 3x to the power of 5 plus 2x to the 3 plus x squared minus 1. We're going to write this in telescoping form. Okay, and so where do we start? The first thing we're going to do is add in any missing powers, right? And so write including missing powers. So we're gonna rewrite P of X is X to the 6, right? Starting at 6, I wanna make sure that there's a power of 5, which there is, so that's good, minus 3x to the 5. And then it skips x to the power of 4. So what I'm going to do is I'm going to replace it with 0 times x to the power of 4. That's true. 0 times x to the power of 4 is 0. So that's why it's gone. Then I have 2x to the 3. That's good. So plus 2x to the 3. X to the 2. Good. Plus x to the power of 2. I'm missing x to the power of 1. You don't want to forget about that little guy. Plus 0 times x, and then minus 1. To write this in telescoping form, we start by extracting the first little x from each of the terms, right? And so what we're going to do is we're going to write x to the power of, oh, sorry, not 6, but 5 minus 3x to the 4 plus 0x to the 3 plus 2x squared plus x plus 0 times x minus 1. So we pulled out that common x from each of these. And then what we're going to do is we're going to do that over and over and over and over again until we don't have any powers left. Well, powers of 1, I guess, are left. So now, bracket, bracket, x to the power of 4 minus 3x to the power of 3 plus 0 times x squared plus 2x plus 1 bracket x plus 0 bracket x minus 1, right? So now I went on to the next group, and in my head, I put brackets like this, and I pulled out a common x from each of those, right? Which is what I did here as well, right? I pulled out a common x from here.
Wait, where did you get the 1 from? Last one?
This one?
No, in the second bracket, the first bracket, I guess.
This one?
Yeah.
Because when I pull out a common x here, then I just have 1 left, or a coefficient of 1. So then here, and then we do it again. Bracket, bracket, bracket. X to the 3 minus 3x squared plus 0x plus 2 bracket x plus 1 bracket x plus 0 bracket x minus 1. Ta-da! And again, where am I visualizing my brackets now? Here. I didn't do it out here, but I'll do it here. There. Bracket, 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 bracket. X squared minus 3x plus 0 times x plus 2 times x plus 1 times x plus 0 times x minus 1. Finally, I'm down to the last little bit here. Bracket, 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 bracket. Whoa. X minus 3 times x. And then rewrite everything you just did. Plus 0 times x plus 2 times x plus 1 times x plus 0 times x minus 1. Ta-da! Telescoping form. What was the benefit of telescoping form? Fewer calculations. fewer calculations for the computer. Oh, what? You want to count the number of calculations? That's weird. You didn't seem to like that in class, but fine. Okay, let's do it. We're going to compute P of 4 using the original form of P of X and how many calculations were required, just keeping track. And then we're going to compute P of 4 using the telescoping form and how many calculations were required. Now, I think what I did in class was I used a line for every little thing that we did. I'm not going to do that because it takes too long. And by that, I mean it takes too many pages. But we can just count them. So P of X was, let's see here. I better just copy. I'll just copy here. So P of 4 is going to be 4 to the power of 6 minus 3 times 4 to the power of 5 plus 2 times 4 to the power of 3 plus 4 squared minus 1. We had to use recursion to find 4 to the power of 6, for example, right? But 4 to the power of 6 is 4 times 4 to the power of 5, which is 4 times 4 to the power, 4 times 4 to the power of 4, which is 4 times 4 times 4 times 4 to the power of 3. Oh, been dropping my brackets. 3. 4 times 4 times 4 times 4 times 4 to the power of 2. I think there's one more. 4 times 4 times 4 times 4 times 4 times 4. My brackets might be sloppy, but they're not. Nice. In the process, we do win because we already calculated 4 to the power of 5, right? Because we used it, so we built on it. So we don't need to do that calculation again. We already found 4 to the power of 3 and 4 squared. And so, but this required how many multiplications? 1, 2, 3, 4, 5 multiplications, right? It gave us a lot of information. 5 multiplications, but it came at a cost. Dun, dun. Then, so we can put these to the side, the powers, the 4 to the power of whatever, they require 5 multiplications. Okay. Then I'm going to focus on these multiplications. 1, 2 multiplications. So plus 2 multiplications. Plus 1, 2, 3, 4 addition or subtractions. What color haven't I used? Sure. plus 4 addition or subtractions, which puts me at 11. Is that 11? 11 calculations. We're not going to win a lot by using the telescoping form, but we know that it should be faster, right? Or at least in terms of the number of calculations, additions and multiplications. What? No way I'm going to write that out again. I'm not going to include the zeros. So I'm going to rewrite it without the zeros. Question? Yeah.
Just a question for the previous one.
Yep.
We got 11. Where'd you get the 4? instead of a-
Oh,
the
here.
4 plus or minus, yeah.
Because I have to do this minus this. So that's 1. And then I have to add this 2. And then I have to add this 3. And then I have to subtract 1. So that's 4.
Oh,
So these 1, 2, 3, 4.
okay.
But then we would be done.
Yeah.
Yeah. So that's where those came from. And maybe I should write it out in words. 4 additions / subtractions. Nice. I'm not going to be adding 0. I'm not going to count that as a calculation because I didn't include the coefficients of 0 up here. So I'm not going to include it down here. So I'm going to rewrite this as bracket, 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 x minus 3 times x plus 2 times x plus 1 times x minus 1. Yeah, the 2 multiplications up front.
Should there be like 3 multiplications? Because that would go up on the equation.
Oh.
This is like 2 multiplications for those 2 brackets. What about 4 squared? Like, would that be another one as well?
Oh, we kind of rolled 4 squared because we had to find 4 to the 6. So we would have started here at 4 times 4. And so that's kind of a win, is when we need to find higher powers, we've already had to find the lower powers to get there. So it's rolled up in this 5 multiplications, right? But we had to go 4 times 4, that's 1, times 4, 2, times 4, 3, times 4, 5. I can't count. 3, 4. What happened? I need a better hand. No, 5, it's good, right? 1, 2, 3, 4, 5. Step away from the plate. Okay. This one is easier to calculate, or calculate how many calculations, in my opinion, because I have addition here. I have multiplication here, addition here, multiplication, addition, multiplication, multiplication, addition. Well, a special case of addition. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 calculations. So we didn't win a ton, but it is faster. And that's what you want to make sure. The telescoping form is always going to be faster, but not a lot. Okay. Good. This is a sequence, but I want to skip it because we're kind of short on time, if you can believe that. Time flies, right? I'll add it to the solutions before I post them. Question or
Yeah,
stretching?
Sorry for the, yeah, this is question two. For the, just that question we're doing, are you adding the brackets?
Yes, because the brackets symbolize multiplication.
Oh, okay, yeah.
Yeah.
So
So yeah, so their multiplication, here's addition or subtraction. And so this way you can just count how many brackets or end brackets you have and how many adding, subtracting you
right.
have. Okay. We want to move on to graphs. How cute is that London Transit System one I found? Here's an undirected graph. First thing we have to do is give the degree of each vertex. Why would we possibly care about that? Right? We need to know if it's traversable or has an Euler circuit. That might be useful, which all relies on how many vertices or how many, what the degree of each vertex is. So let's start there. Let's do vertex degree. A has degree 1, 2, right? 2 things coming in and out. B, I'll do B, C, D, E. Oh, that looks bad. B has a degree 3. C has degree 3. So let's write those down. 3, 3. D has degree 4 and E has degree 2. Is the graph traversable? How do we know? It's traversable only if you have 0 or 2 odd vertices or odd degrees. We call them odd vertices, but we're referring to the degrees. We're allowed to have 0 or 2 in order to be traversable. Now I have 2 odd vertices. We have 2 odd vertices. Therefore, it is traversable. And I'm using this little table that we made. Where is it? Here. In the graph section, right? The number of odd vertices, 0, 1, 2, 2 plus. Traversable, what does traversable mean? Means you can trace each edge without tracing the same edge more than once. Vertices may be passed through more than once. So if it has 0 odd vertices, then it is traversable and you would start at any point and you would end at the start. If you have 1 odd vertex, then it's not traversable, so you can't do anything. If you have 2 odd vertices, then it is traversable and you're gonna start at one of the odd vertices, and end at the second odd vertex, right? So that's something worth committing to memory, I think. Okay. The explanation is we have two odd vertices, so it is traversable.
Oh, I just one question.
Yes?
Can you just go back to how you got the numbers for A, B, C?
Oh, yeah. I'm counting, so A has two things, so it's degree 2.
Oh,
B
okay.
has 3 things, so it's degree 3.
Oh, okay, that makes sense, yeah.
Yeah. And then you go through each of them, and then you're paying attention to how many odd vertices you have.
Right, yeah.
Yeah.
It's odd just because two letters have the same number.
Well, it's odd because 3 is odd.
Oh, okay.
So
Oh, it's
B,
odd number, yeah.
B and C are odd vertices. Does the graph contain an Euler circuit? Explain. No, it doesn't. In order to be an Euler circuit or to have an Euler circuit, then you have to have 0 odd vertices, right? Because it has to be traversable and it has to create a circuit. No. I'm trying not to say we have 2 odd vertices because then I'm kind of just saying it again. You can if you want, right? That's true, right? We have 2 odd vertices and that's why, but let's flip it the other way. No, to have an Euler circuit, it would need to have 0 odd vertices. Therefore, it does not contain an Euler circuit. Good. Does this graph contain a Hamiltonian circuit? If so, write a potential circuit. When I say write a potential circuit, that means that there are many potential circuits. What does it mean to have a Hamiltonian circuit? Right, an Euler circuit is when we cross each edge exactly once, right? And you're allowed to go through the vertices, but now a Hamiltonian circuit is flipping it, and now we're talking about only passing through each vertex once, but we can reuse edges if we need to. So I'm gonna grab this image. As long as we remember what a Hamiltonian circuit is, then we could, where could we? Oh boy, I had one mapped out. I guess I could go Hamiltonian. It's like Hamilton, yeah.
So just the opposite of an Euler circuit.
The Euler circuit talks about the edges. And the Hamiltonian circuit is for the vertices. So you're only passing through each vertex exactly once, but you're allowed to recycle edges, which is hard to do, but you're allowed. And now I'm blanking. I had one mapped out. What if I start from, I feel like I started from B. B to E to D to C, no. It's when I should really have it mapped out. I felt like I did it. I was like, oh yeah, got it. Moving on. What if I start at C? Maybe that makes it better. Do you guys see one? I don't have anything. Flying blind up here. How about, let's try C to D, oops, C to D to E. Oh, doesn't want to do it. C to D to E to B. I want a circuit though. It's not going to do it, but I think I'm on the right track from D. I think what I'll do is I'll give you the starting point. Then it'll be easier, but I don't have the starting point. So then I'd have to try all these. How about D to, no. TBA. I'll find it. I have it written down somewhere, but I don't have it in my brain. Unless you see, I'll go to the Zoom and see if there's anything in the chat. Nothing. Had it. Unless I'm forgetting that it doesn't need to close, but a circuit has to close, right? So that feels weird. I'm out of time. Can you believe that? Let me just blab about the rest of them. Here's my cute little underground. Is it traversable? What are you going to do? Count the degrees of all the vertices, right? It's only traversable if you have 0 or 2 odd vertices, right? And you've got the starting endpoints. Traveling salesman problem. How many unique routes are there? N minus 1 factorial over 2, right? And then you're going to list all those. That's only 4 minus 1 factorial. So 3 factorial, which is 3 times 2 times 1, which is 6 divided by 2, which is 3 unique routes that you're going to find starting in Denver. That's nice. And then you're going to find the distances of each route and find the minimized distance. And then some more. Nearest neighbor method. Kruskal's algorithm. You're going to make a tree, a minimum spanning tree, by removing, or maybe not removing, but by adding the shortest edges slowly until you have how many edges? N minus 1. Then it should be connected. And then this is the same. And then you're done. And then you're all studied up for the test. No class on Monday, obviously. See you for the test on Friday. And enjoy your long weekend. There.
Are the answers going to be on the Moodle?
Yeah.
Oh, okay.
Yeah, I'll finish them up. And I'll stop this recording here.